Hello, are you able to hear me? Hello?
Yes, sir.
PPT?
It's visible, sir.
Yeah.
Okay,
Vijay.
thank you. Yeah, thank you. Sorry for the delay. Actually, there is a small problem here at our institute regarding internet issue. So now it got resolved. So then let me start, or let me continue at least, because of some people at the time only some people are there. Let me start from the beginning. So then in this presentation, I'm going to cover the 4 3D printing types, that is VAT photopolymerization process, material jetting, binder jetting, and material extrusion process. And rest we will see in the tomorrow's session. And if you see the classification of these 3D printing technologies, the early classifications from Marshall Burns during 1993 and as well Croth 1998. So similar classification given by these two people, that is based on the technology. Say for example, if you are using a laser based technology, so they grouped all that into one category, and printer based technologies, they made one more group called a printer based technology, and extrusion based technology. Like that, they have classified the 3D printing or additive manufacturing systems. So then Chua Chikai, so from Singapore University, the Nanyang University, he has given a different kind of classification that is based on the raw material form. So this is very famous classification given by the Chua in 1998. So if the raw material is liquid, and then he has grouped all the technologies under that liquid based system. And if the raw material is a solid based, and then he have made one group called solid based and powder based. Even though powder is also solid, but it is in a granular powder. So then he intentionally created powder based as one category. So this is the Chua Chikai classification. So, but there is a conflict here. So then ASTM has come out with a different classification. Before that, the DT form also slightly modified the Chua classification. So by again, the raw material is also in one axis, that is a liquid polymer or a discrete particles like a powder or molten material and solid sheet. So that is on the one axis, and on the other axis, so he has introduced the other dimension is whether it is a 1D channel, means a single source of either laser or a extrusion, means you have only a single point here to deposit, and then you have other one as two to 1D channel, means you have two laser guns, say for example. So then it is a dual laser, or it is basically a 1D channel, but the twice the productivity. So that is the thing. And then next one is the array of 1D channels. Say for example, you may have it is quite similar to the inkjet printing technology, where you have the nozzles. They have put it in a row. So like where your inkjet printer consists of the array of nozzles or the orifice. So then you will be jetting the material from that nozzle. So means the productivity is improved here. Then one to two times, and here it may be 256 or 512 times got improved during this array of 1D channel. And further, people has come out with entire layer is exposing in a single attempt. So means it is more faster than the previous one. And we don't know what is going to happen. That's what in the future projection also we are discussed in the first session. That is, it may be a Waxel based. Waxel is a 3D thing, which we don't know. Very soon we may see some 3D channel also here. So that is the developments under these technologies. So then ASTM on seeing this, then they have classified these technologies into 7 groups, and today we'll see the 4 classifications, and then tomorrow we'll cover another 3 classification of this technology. And let me start with the first process called VAT photopolymerization process. So of course this is the first technology invented by Charles Hull from 3D systems. So it was the technology called SLA. So the name suggesting you that, so there is a vat. So means the raw material is taken in a vat or a tank. So vat or a tank, the raw material. Of course, the raw material here is plastic only. The plastic, and that is a thermoset plastic. So that is taken in the liquid form, and that too you are putting it in a tank, and then which we can see this term photopolymerization means your raw material is photosensitive, means once you expose to light, so it will start solidify. So that is the meaning of your photopolymerization process. So basically it works with the powder chemistry called photopolymerization. So you take the raw material as a liquid, so then you start polymerizing, or you start exposing that liquid against laser. Actually here you have a three kinds of systems here. So whatever I am putting here is up to date technologies under this. So SLA is the earlier technology. Used to use only laser here, but here if you see these other two, DLP or CDLP, so the raw material is same, the photosensitive polymer, but how to exposing this raw material, that matters. Say in SLA you may be using a laser. Again, laser is a single point laser, but here you may be using a projector, maybe LED or LCD kind of a projector. You may be using it here, and you may even use LED plus oxygen here. So we'll see in detail about all these technologies, but basically if you see the transformation, otherwise you put it into a three generation machines. The first generation is very slow. Why? Because it's a single point laser you are using it. But second generation a bit faster because of the projector here instead of a single laser, and then light entire layer you are able to cure. And here of course you may have oxygen also, it have its own identity. We'll see what is that. So basically it has a lot of improvement. So from here to here, so it may be 40 times minimum, 10 times is faster this machine than this one. So like that. So then we'll start with an SLA technology. So what is an SLA technology? So as you know that SLA technology, where the Charles Hull invented at the time, so he took the photosensitive polymer resin. So this is the model and this is the support. So which it made the model and support. So here like any other process, so you have to start with the CAD model, right, and then slice it and send it to the machine, and which you can get these prototypes. Basically it was a prototyping technology, so now it has matured, but anyway still the prototyping applications are more for an SLA. How it works? So as I already mentioned, the raw material is a liquid form, and use a laser to cure as per the design or as per the slice data. So what we have to do is first we have to start with a solid modeling software to make the CAD model, or even a video gaming data or whatnot. It may be a medical data or it may be scan data, but you send that thing, and then you have, based on that cross section, now you can see. So it lay a thin layer of the liquid. So from the software it is going to get the instructions, and now you can see the recoater is laying a thin liquid film of layer, and now we can see the laser is going to solidify as per the cross section. So it is now basically it is a polymerization process. You have a monomer as a raw material, and you have light and catalyst, so it is getting polymerized, so which we can see, and one layer is over, and then second layer the recoater will sweep, and then it will be ready for the second layer, and again the laser will come and it will cure the cross section. So based on the cross section your laser, so finally you are going to get this kind of a model. So you start with the liquid photosensitive polymer resin, and then you end up with this kind of a model, so through a laser. So then what is the difference between, say, SLA, DLP, and LCD. So basically, just now whatever we have seen, that is a laser based system. So laser will have only a single pencil like rays, but whereas DLP, so DLP is like you have but any, as usual, like it should start with the CAD model. So then you take the CAD model, slice it, see how fast it is. So SLA can able to print one, but the same time DLP or LCD can produce 40 layers, means it's a 40 times faster. How it is possible? So you have a projector, so which it's going to project, rather than, so entire layer you are able to done in a single go. So with the help of the conventional projectors, maybe LED or LCD, where you use for the display systems, here also you are going to use the same technology, the DLP or a LCD kind of a technology to expose your light onto the liquid. So first we'll talk about a DLP, that is called a digital light processing. So then your DLP printer uses a light projector, so which will print or which will project onto the say what you call the optics or the projector, and then as for the cross section, so it is going to be cured. That is going in a single go, so your entire layer is getting done, rather than doing laser with a single point. So you have a projector, so with an optic system with the projector, so which you can able to get entire layer in a single go. It's very faster. And of course, similarly you have the display system LCD, and here the same LCD technology, so you are going to use to print this, and then you have, instead of a LED, you have a LCD here. That's it. So only the difference, like how your cell phone is working, and similar way, so your printer is printing layer at a time by exposing the light onto the screen, and you are going to get the each layer, so like one by one. So you have a bit disadvantage of LCDs, but LED may be the better, or kind of a thing. And of course, yes, SLA it may use laser, but it's slower. Why? Because it has to go point by point, rather than basically it is a single point laser. So it will take a lot of time to process the same layer which we are talking about, the same cross section. It may take longer time. So this is the basic difference between DLP, laser, or LCD technology. So then what about this, the third one? The third one, whatever we have seen, it's a DLP, that is a LED or LCD, will be used as the energy to cure the polymer. And here you have from carbon 3D, there is a slight difference. They are introducing a oxygen here to get a kind of permeable kind of oxygen layer or a dead zone. So as usual, it starts with a CAD model. Say this is one of the case study where it is showing a functional part. It's not a prototype. It's for a screw compressor rotor. So this is a screw compressor rotor they design, and then they fabricated and they used for the application. It's end usage, say where it will go and fit here. This is the compressor screw, so where it will go and fit. And then so then you have a CAD model, and then you send it to the machine after cross section slicing, and where you have this is you have a projector here at the bottom. So from the projector, so you will be projecting the light. So through this light engine or a projector, so you are able to project onto this liquid, and you are creating a thin dead zone, or you are creating an oxygen permeable window. This is a window which is transparent, or it is a light sensitive. Why? Because it has take the light. At the same time, it is oxygen permeable window, and where you are creating a dead zone here, a very slight dead zone, and then just you keep on supplying the resin, and just it will be dragging on. It is something like if you see a movie in Terminator, how it will be, your this Terminator, how it will be formed. And similar way, you can get, it's very faster, where you will be keep on supplying your resin and through this dead zone, and then you will be pulling this thing on the top side. And here we need to go with the post curing also. Why? Because any VAT system, so it has to undergo a post curing operation called, so we need to use a UV light for further curing. Why? Because we are going to get only 95% solid, but it's not 100% solid. Still there will be a viscous material is left out. So in order to make it 100% solid, so we need to, every time every part should be cured. So that's about this technology, where it is very faster rather than, and not only faster, which you can see it is using direct part, the functional part, it can be sustaining. It's not a prototype basically, so it is a end part. So these are the developments under this VAT photopolymerization process. So first generation printers, so where you have only the laser, it's very slow. And second generation printers, maybe you have a projector. And then guys like carbon, they have introduced, but oxygen is inhibited to the light, but they have made that as advantage, and they are making that advantage and making it as, now it may be 10 times or 20 times faster than the existing systems. Anyway, SLA, just now we have discussed. So SLA was a technology patented by Chuck Hull or Charles Hull in 1984, and first 3D systems in 1986. And just now we have seen it's a liquid based photo curable resin, and photopolymerization is the process, and thermoset is the material which you are using it. And these are some of the parts. And the first video, exactly this is the working principle of the first one which you have seen. So you have the raw material in a vat, and you have a laser, and you have a galvanometric mirror to scan onto the surface of the liquid. And of course DLP. So basically we can classify these VAT systems into three categories. Just now we have seen. So you have a Form Labs, that is a one company. This is a desktop SLA system, so where you will be using a laser scanning. So maybe the build volume around 145 by 145 by 185, and you have an LED or LCD kind of a projector. And if we compare the cost, so main intention of keeping this slide is, if you see the cost comparison, so it is $3,500 US, and it is $279 US. The LED or LCD, it's very cheap, but dimension may be a bit less in x-axis. And then 3D systems, on par with 3D systems, high-end machines, so it is almost 100 or 1000 times costlier than these desktop SLA 3D printers. So yeah, on the video also we came to know that there is a projector, and which it will project onto this liquid on the surface of the liquid, and you will be, basically it is a bottom up approach. So normally SLA is a top down, so it may be a bottom to top, it will go like first it will go, and the build platform will be moving upward rather than the downward in case of SLA. So, and then what are the so FDM and SLA, if you compare, what are the issues here? So the main issue here is entrapped volume. So that is the one concern here. But FDM, it doesn't have entrapped issue. Why? Because as for the demand you are supplying, but here it's you are immersing, you are lifting the part from the VAT, so that may be creating entrapped volumes. And of course you have a very good advantage of SLA if you compare with FDM. So you have 25 to 30 a micron layer thickness, in contrast with 250 to 300 in case of FDM. So that is the biggest advantage, where you can get very good resolution in case of any VAT system, either it is SLA or a DLP or it is a carbon 3D. So you have a very smooth surface. Among all the polymers, you are going to get the best surface finish with the SLA or any VAT system. Coming to the materials, you have a rigid material, flexible material, colored material, high temperature material, dental grade, and of course you can go with the ceramic and metal also, but not directly. So then we need to go with some furnace treatment by sintering it. So you can even use a VAT system for ceramics, printing ceramics and metals. So that's what actually I was trying to put it as a classification into metal printing and ceramic printing, but I could not. Why? Because nowadays the technological growth. So now with the SLA, you can able to not only polymers, you can even go for the ceramics and metals. Even the case for the FDM also you can make metals now. So then that's what I could not put it in a material wise my classification. Then I stick to only the ASTM standard classification, that is 7, and today I'm going to talk 3, and tomorrow I'm going to 4, and tomorrow I'm going to talk 3. So that's what I could not group them in a metal or polymer or ceramic or composite. This is the reason nowadays this technology is not restricting to only polymer or metal or ceramic or composite. So that is the wonderful development in this 3D printing era. So of course, just now we have seen a clip as a carbon technology, and Nexa is another. It is almost say 10 to 20 times faster than SLA, the kind of technology which you are using it in case of DLP or a carbon 3D. It's very faster. So coming to the carbon 3D, just in the previous video we have discussed. So you have an oxygen permeable glass here, and you're creating a dead zone, and then it will be, which we can see it is very faster. And not only faster, as usual, like you can make any lattice structures, which you can see. You can come out with some kind of innovative products, like something like this is a helmet which is inspired the lattice design, where it can take maximum shocks than a conventional design. So that is the invention. And of course, similarly for the footwear, so when athletic, even if you make it like a lattice, you customize as for its pressure points. So that is a wonder where this technology, none other than this technology, will give such kind of customization any area, maybe footwear or maybe helmet industry or whatnot. So everywhere, so which we can see, this is the speed time versus technology. It is taking a longer time. The SLA is taking a longer time. SLS is also, PolyJet is also, and which you can see DLP. So it is almost negligible, 10 to 20 times faster this technology than the first generation 3D printers. So then I'm talking about even it can print ceramics. So then how to print ceramics? So how to print ceramics? So you have just you mix your resin into with a what you call the ceramic powder. So basically you will be mixing your polymer with the ceramic powder. So the mixing of the ceramic powder and UV resin will be taking place, and then as usual you start with slicing design, slicing, and then which we can see 30 to 50 micron size thickness, which you can adopt. So then of course you go for the printing. So you print. So here what you are going to do is, here you are bringing the raw material, basically it's liquid, as you know that, and then you will be bringing like a slurry along with the ceramic, and you will be pumping continuously here. So the circulation of this printing liquid will be done, and simultaneously your projector will project, and then it will take the cross section. So like that, so it will start from bottom to top approach, that it will go, and then we need to go with the debinding. Means you have a polymer inside, so along with the ceramic, so just you can evacuate or you can debind that plastic binder in the debinding treatment. So just you debind, and once you debind, you will be having a evacuated space. So then you put with the sintering furnace, just you put it in the sintering furnace as for your proportionate value, you can put it, and then your ceramic is ready now. So that is the beauty of this technology, where people used to talk about only it can produce only polymers. No, absolutely, now it can be extended for the metal also. So not only ceramic, the same logic can be extended for the metal. So instead of ceramic powder, you add the metal powder, of course. So but it should be followed debinding and sintering. So these are some of the ceramic components and some of the investment casting patterns, and further it got branched cast part. So like that, we can talk about these SLA DLP technology. For the ceramics also it is possible, and similar technology exclusively for medical applications or exclusively for dental applications, where ceramic is the very good material for the, especially for the dentist. Why? Because your teeth will no, it's also a ceramic material which it's going to mimic. So then again, use the same, start with the slurry and use the light to sinter, or sorry, the cure, and then you do debinding and then sintering. So your ceramics is ready. So you have a ceramic static mixer here, and is a dental where you have bone got augmented with this ceramic implant here. So it is made out of either hydroxyapatite or tricalcium phosphate, and which we can say other dental restorations. Either it is made out of a zirconia, or these are the crowns. As you know that it's zirconia, it's a ceramic which you can print it directly for the implants. And even you can go with other ceramics like aluminum oxide, zirconium oxide, silicon nitride, hydroxyapatite, tricalcium phosphate, and silicon based ceramics. So this is about the ceramics part. So that's all about the VAT system, and then we'll move on to the material jetting system. So basically, what is the difference between the VAT system and the material jetting system? Almost the material may be the same, so which it may be a photosensitive polymer resin. So the same material, instead of taking it into a vat, so can we jet from the nozzles? So that is like something like your inkjet printer, how it is jetting. The similar way you are going to jet the material, again the same material. Say in case of material jetting, the material is a plastic, that is a photosensitive polymer resin, and instead of taking it vat, so you jet from the nozzles and simultaneously use a UV light to cure. So you can very well demonstrate this through this video. Like you start with the same raw material, but don't pour it into a vat, but you jet from the nozzle like your inkjet printer, how it will be jetting. So here you have an advantage of jetting it. Why? Because you can dedicate some of the nozzles into one material and other row of nozzles for the other material. So there is a provision here. You can go with the multiple material printing. So which you can see there is a one object here. So you have some flexible material, something like this, some buttons. Say for example, you have your remote this one, the TV remote. So you see that the buttons will be more flexible than your body is rigid, something like that. Say you have a combination of rigid and flexible, or it may be opaque and transparent. Why? Because you have a different colors also here, so which you can use the different colors of the material to jet from these nozzles. So these nozzles may be 500, or it may be 1000, or it may be 2000 or 3000. You can scale. There will be a chance to increase the scalability of these nozzles. So you jet the material from that nozzle, and simultaneously you expose, and you are going to get again the same principle of polymerization is going to work here. So as I already mentioned, like your VAT system, this is also giving the best resolution and the best. Of course you have a more advantage, like it's more faster than the especially SLA. It is more faster than that. And then you have these full cure resins here, which we can see. Then you can load them or you can unload them, so during printing. So then you have that kind of a flexibility here. Say because of you have more flexibility towards jetting the nozzles, so you vary the material. So how you will be varying here, you have two materials here. It's not only color, I'm talking about different properties of the material which you are going to jet from it. And you have in support structure something like a wax, or a similar to wax kind of a material will be used as a support here, which you can see that supports at the bottom. So you will be jetting, some nozzles will be model and some nozzles will be support, and you will be jetting simultaneously wherever you have model, and those nozzles will be activated, and wherever you have a support material, those nozzles will be activated, and that will be jetting onto the substrate. So this is what it's going to happen. Then just you can remove this and you can clean this tray, and then further you can use some water jetting kind of a stuff to further remove your supports, or to clean the surfaces of the part which you got fabricated. So then use the water jetting method to remove the supports fully. So like this, you can make these parts through this polyjet technology. So basically it works in that way. So means here the biggest advantage is you can go with the multiple material option. So that is the biggest advantage of this material jetting process. And then you have very recent development under this material jetting is nanoparticle jetting, called NPJ. So even you are able to jet the metal here. It's a plastic simply, but it's a metal. There is a company called XJet. So you are jetting the metal particles, nano particles, and you will be curing with a heat. Actually here there is no laser here. So basically the the biggest challenge here is how to get a nanoparticle metal powder. So that is the thing. So then you even this can be printed a metal parts, which you can see it is preparing the metal particles, nanoparticles. So which you have some atomizers to do that. So just you can make the metal particles of nano-sized metal particles, and you are going to jet through these nozzles. So again, same principle, it works. Instead of a material in a polymer state, here the metal will be in that state, and you will be jetting the metal particles. So which you can see from that nozzles. So you are jetting the nano-sized particles. And of course, we need to start with the software, and you have a support, and you have a more metal will be the main, and support normally it may be a ceramic support will be given. So then you print them so through these nozzles. So just once you prepare this nanoparticle and then just, of course it's a metal, you have to operate at high temperatures, maybe 500 or 600, or it may be above 1000, depends on the material which you are doing it. So then you have this material, and then you will be jetting it. So it is very faster than the powder bed system. So everybody is now targeting to metal powder bed system. Why? Because it's very costly and slower. So now it is very faster than the powder bed system. And then this is what you are going to get, that's droplets of metal, and then it will be with the liquid, it will be thing. And then here the biggest advantage, further you are able to reduce your layer thickness. So 250 in FDM, 25 in SLA. Now it is 2 to 5 microns I'm talking about. That is a layer thickness which you are going to use here. So that's about the metal 3D printing under the heading of material jetting, right? So that is the development is happening nowadays. And of course, you have a bit older technology. This is a drop on demand with the wax material. So you can apply the same logic for the wax. So you start with the wax. So taking the wax as the raw material, and then you can heat, and then you can put the wax, and then you can heat the wax, and you can melt it, and you can jet it from the nozzles. And simultaneously here you may be milling also. Here basically it's a wax, it's a softer material. So it's kind of a hybrid process, which you are going to use a small milling cutter also to mill the excess portion. So basically wherever you have staircase right now, which you can see there is some staircasing effect. So every time, every layer, it will be milled. So where your the accuracy will be improved. Why? Because it's going to use for jewelry, or basically this investment casting applications you may be using it. And you have the model and you have a support. So just you remove the wash away support, and then you will be left out with the model. So that is a wax based pattern. Now you can link with your wax pattern to the investment casting. So then you can make use of this as a master pattern, and this is a wax pattern, master pattern, and then you can create your investment casting tree, right? So then you can create the slurry, you add the slurry, right? And then you can pour your the metal now in this thing, and it will get solidified, and just you break this mold, and you will be left out with the metal part. So this is what use normally jewelry or dentistry. People are using this technology for making implant in case of a dentistry, crowns, dental crowns, or any other metal, and which it is coming through casting route. So these are the some of the developments are almost up to the date. These are the developments under material jetting system. So just we'll see what the material jetting system. Of course, this polyjet is the technology invented by Israeli technology, but now it got undertaken by the Stratasys. So as we know that we have a flexibility here, you can go with the colors and multiple materials. Somewhere it is flexible, somewhere it is rigid. So you can combinedly print it in a single go. So that is advantage where you can, of course, which you can see these many number of colors. So these many number of colors, which you can mix it something like your paintbrush, which you will be taking a natural colors and mixing it. And similar way, which you can beautifully, you can see how beautifully an anatomy of a medical community, which you can give for the teaching aid, right? So they can explain these anatomy So instead of taking a cadaver bones or a kind of a headache, why? Because you have to maintain them, keeping it in a solution. So there will be a huge procedure, and it may get some bad smell also. But here, no such issues. So it's a very good tool for them to use this kind of thing. Of course, it's a multi-jet printing called MJP, and sometimes polymer plus wax. Just now we have seen XJet, so you are able to print the metal and as well ceramic. So Aerogel is another technology from Optomac. So this is for exclusively for electronics, making a smartphone antenna. So again, it is a nano based. So you are going to create an aerosol kind of a thing. So just you will be taking, again, you have to have some atomizer to atomize your liquid particles to the nano sized thing, and then you have to jet from the nozzle. So here this is coming in that way. So then you are in the atomizer. So again, you will be atomizing these liquid particles, and you will be atomizing it to a very nano sized particle size, and you will be passing through that through this atomizer where you develop that nanoparticles, and you will be taking these nanoparticles to, you have another process here called as which we need to remove some oxygen. There will be a gas may be entrapped in this, so then you use some kind of no mist here, then from the mist you have to remove the oxygen or any other particles or oxygen or any other things. So then it will be 100% pure, and then it will be coming from the nozzle through this depositing head. And of course we need to have some stored gas to in order to avoid the clogging of this in the nozzle. Then you will be pumping the stored gas. It is something like, looks like your DED system, but basically it's not a DED, but almost looks like a DED system where you will be pumping the powder, but here no powder, nothing. It is a kind of nanoparticles you will be jetting along with the stored gas, and it will be jetted, and it will be, so which you can see these are the electronic equipment where from the Optomac, this is the aerogel technology. So this is what it's happening under this material jetting system. And of course, which we have seen the exit, so it is very faster, high speed, 5 times faster than SLA, and smooth surface. So and then the low shrinkage, if you compare with, it is almost similar to the metal injection molding, but it is 8 times, no, it is a 8x faster than your metal injection molding, you remember. So that is the advantage if you compare with a conventional metal injection molding. And then you are going to have isotropic uniformity and a 99.9% dense. And of course it may support several materials, metal as well ceramics. So depending on that material, then you have to operate at the high temperatures. And then you have another technology from Wader. So it is a similar technology. You may be taking the raw material as aluminum wire here, and then that wire will be melted, rather than you will be creating a kind of the metal, molten metal, you will be depositing it here. So this molten metal will be deposited. So it is very faster than the powder bed system. And again, people are targeting, why? Because powder bed system is very good as far as so far for the metal printing, but now people are coming out targeting to these the laser based powder bed systems. So now people are able to jet this molten metal, are taking raw material into this like a wire form, so either aluminum or any metal. So this will be very easy, right? And you melt it, and then you pass it through this nozzle and you spray it. So this molten metal will be sprayed, and of course you need to have a harder nozzle, maybe ceramic or some harder material. So then it will be jetting from that, right? So this is a molten metal, it will be jetting from it. So where we can see these are the metal parts it got printed. So it is so wonderful development under this. So people may think that every time binder jetting or metal jetting, it will print only the polymers. No, so you can even print them as a metal or ceramic. So that is what the developments are happening now under this. So the kind of jetting technology, say where you can see aluminum, titanium, you have iron, chromium, copper. So where these are the high temperatures which it's going to work. So and then the material preparation of the material into powder is very costly. And anyway, we are going to have one session, exclusive session on that, how to make these powders through atomizers. That's a very costly process, but we can take a wire. It's relatively very cheap. So of course you have other issues, you have pros and cons also, but anyway, this is about the you have other similar technology which is called a Joule printing. So where again the it's in the real time, it's very fast, it may be more than 2 kg per hour. So it is something like you can target to DED system. It seems like DED or a welding technology where you have speed is very low, DED or a powder bed, but it's very faster. So like it may be almost competing with the welding, conventional welding process like TIG or WIG, MIG welding or TIG welding. So that is the beauty of this technology, where you can see the Joule printing. So it is printing the metal directly from the metal rod, and you will be now able to print that, or you melt that rod, and then you are able to deposit through the nozzles. That's what is coming under jetting. It's a Joule printing of metals. So of course, XJet, you have the combination of metal and ceramic. So you can print steel as well as ceramic. So that is another beauty of this technology. And then let me move into the other technology called the binder jetting, the third technology. So what is the difference between the material jetting and the binder jetting? So of course, binder jetting, the name itself, you're not jetting the material, you're jetting the binder. So there won't be any laser here. So your binder is going to be the glue or agent to bonding agent to get the bonding between the either powder particles or any other form. Say under this, the binder jetting technology has started with Z Corp machine, and again it has originated from MIT. So MIT has sold patents to 5 different companies. One among is Z Corp, but now Z Corp is merged with 3D Systems, and you have other companies like X1, and you have Voxel Jet, and you have Pro Metal. There is another company. So you have, and 3D Systems, of course. So they have these binder jetting systems, the raw material here, and then which we need to talk about this guy, that is HP. As you know that this guy is very good as far as 2D printing is concerned, but he has lately entered into this market. And of course there is a technology called multi-jet fusion called MJF. So again the material may be plastic here, but you may get different colors. We'll see that also how it will work, but running short of time, I may be skipping here and there. So why? Because we are already in the late. So let me try how best I can present all these technologies, right? So of course, which we need to talk with the Z Corp powder based system. It's the first generation of machine. So which the raw material is powder, and then it will be spread, and then binder will be sprinkling from this nozzle, and that binder will be sprinkled on that on the bed of powder, and where it will be absorbed, or rather than you have a fusing between the powder particles through this binder. So again, you may have a different binders. As for your material, you have to choose the appropriate binder to stick the powder particles. So once you have done this, and then you evacuate the loose powder and take out the part from the cake, and then you use some kind of post processing. Of course, this is only one technology. There won't be any phase changes happen. So then we need to much worry about the post processing. We have to go depends on application and depends on the material which you are using it. So then you have to go with the post processing process. It's a compulsory in order to enhance your mechanical properties, in order to enhance your quality of the parts. So then once you do, and then they will be giving some kind of coatings or some kind of what you call sintering agents to improve the mechanical strength. So or some wax coating sometimes for the better appearance. So even can be coated with the wax for the during the post processing process. So then you can do that one also. So basically this was the first generation machines where the raw material may be either a kind of an organic material like a starch, or it may be even a polymer, or it can be a sand also. And now recently this X1, they have come out with the sand cores and sand molds. So ceramics, a bit of ceramic materials and sand molds and sand cores. So you can make these big size sand molds and sand cores. So you take the raw material again. It's in case here is the powder is in a sand, like either a silicon based or a zircon based sand, and then you spread like this one, and use, of course, use the binders to jet the binding from your nozzles. So these, which you can see, those are a set of nozzles where I think it may be millions of droplets will be per second. You are able to jet it. So then you can make very big size engine block, something like this. So then you can make any large size components. This is the core. So you can make this sand mold sand cores, and further you can link with your foundry application, like where you can use for the sand casting applications, right? So basically, as I already mentioned, so it will start with jetting. This is the raw material, the powder. It is recoater will be putting a layer of this sand, and now which we can see this is going a layer by layer recoating it. So normally it will be 2 layers, it will be recoated, and now you can use your binder. So the binder will be sprinkled from that nozzles, so it will be depositing. So where you can see that binder will be depositing right now. So it will be printing the binder onto the already pre-laid what you call the powder bed, and now we can see this liquid binder is coming, and then it will be going inside that powder particles, and where it will get settled down, rather than where you can get the fusing of these powder particles is happening because of these binders. So where it will go, and the powder, how you will make, and what kind of spherical powder, and you have a lot of parameters to take into that. But anyway, so it's the thing where you can do this kind of basically this is for sand molds and sand cores for and similarly you can take, instead of sand, you can use a ceramic powder or even a metal powder to do the same, but we need to go with the sintering process after it has made out of it. And even you talk about from the X1, so there is a metal which is almost similar. Instead of here the earlier one is a sand, now it is a metal. So take the raw material as a metal powder, and similar way which you can jet the binders, and from the binding where you can get this bonding, and take out this green part and put it in a furnace, right? And then you will be getting 99% dense. After putting it in a furnace or after doing the sintering operation, you are going to get a dense part. And of course, let me talk about bit the last but not the least, the HP technology. So HP technology is one. So you have this material again as the raw material is a powder, of course. So the raw material powder, and basically it's a polymer, it's not for metal. So of course it has to start with the CAD model. And the beauty of this HP is they are very precise in printing, 2D printing, and of course they are maintaining that quality here also. These are very precise. In order to get the precise one, they have come out with 2 agents. One is a fusing agent, another one is a detailing agent. So fusing agent for bonding purpose, and detailing agent is for increasing the resolution or getting more appearance or your colors, right? So you are going to have a different colors. So then your detailing agent will enhance your the properties of the part. So this is about the HP technology. So and these are the developments under this binder jetting system. So then, as already mentioned, MIT has invented this technology during 1997, and plastic powders were the material, and printed, of course, the binders color one, and you have infiltration to improve the strength, and no supports are needed. So, and just now we are seeing the same X1 technology. You can make the sand mold, sand cores, and further you can make the metal parts. And similarly, Voxel Jet is another company which it's almost similar to the previous one. Why? Because the patents got sold to the 5 different companies. The MITs has sold 5 different companies, and one among is the Voxel Jet. It works with the same principle, whether it's a Voxel Jet or the previously X1 or a ProJetal or Z Corp. So then you can go with a metal also here, of course. So, and just now we have talked about the HP. So you have even ceramics can be jetted. So you have a binder jetting, but ceramics, of course, ceramic or metal, we need to go with the debinding, and further it is sintering. So which we can see these are some of the ceramics. So of course, the same metal, same logic will be you print them first and debind it, sinter it, and then finally you have your metal part out like this, right? So then let me have my last topic is extrusion based systems. So these extrusion based systems, so you can so of course FDM nowadays is very popular. Why? Because the Scott Crump patents got expired, then everybody now you have a DIY kits. And anyway, Rakesh is going to next session will be on DIY kits, how to assemble these and how to integrate your software, how to integrate your hardware, and how to integrate your firmware to make a DIY 3D printer. So now that is the status of this extrusion based system, especially for the FDM. So started with plastics, composites, now you are able to print the metals also. That I will discuss that also. Then people may think that FDM means only polymer, PLA, ABS. No, it can print now metals, composites. So remember. So then you have, of course, this technology started with a technology called Stratasys from US, where the Scott Crump has filed the patents on this technology. Once the patents got expired recently, not recently, 10 years ago, then your duplication, replication of your technology has started. So which you can see, I think everybody may be familiar about this technology. You have one model head and you have other support, and then you will be bringing the raw material in terms of spool. One is a model, another one support, heat it, melt it, and bring it from the nozzle, and then you come out, it will come out like a liquid state. Then it will fall onto the platform, and one layer upon other layer. It is something like your jalebi, how you'll make, right? Exactly, but it is not your hand in the jalebi or in your mehendi. You will apply through manually. You have the degrees of freedom of your wrist or hand you apply, but here everything is computer based, and as per your G codes. And then of course supports are the concern here, which we need to remove them, whether it is a breakaway supports or it can be a soluble supports. Just you can dip it into the water, and then you will a water kind of a solution. So there will be a solvent which is compatible with your support material, and it will dissolve. So that's about this FDM technology where everybody knows about. So then recent developments under this is composites. So there is a company called the Markforged. So Markforged, so they have come out with these filaments, but you printed them, and then you can even create your what you call carbon fibers will be reinforced. You print with a nylon, and then it contains your carbon fiber things which we can see. So then you can go with the carbon fiber or fiberglass or a Kevlar or fiberglass. It's HSST. I think Rakesh has covered all these materials. Say you can talk about these. This is on par with the metal also. Then people are saying, quoting that it's a lightweight, and as you know that the advantage of any composite in a conventional making of a composites through wire binding or any other technology, we know it's for the aerospace or any other lightweighting applications. So definitely you're going to get that kind of advantage here also. So then you can use this technology especially for these kind of a composite applications. So then this is about the composites from FDM technology from the Markforged company, and that is for composites. And similarly we can discuss something about metals, and of course there is a company called Desktop Metal. So Desktop Metal is now saying that through extrusion you can print your metal. So that is the thing. So it may go with a bit again. So it is not a direct metal you are going to get it. Of course, it should undergo a sintering process, and of course it must have a debinding and then further followed by sintering. So which you can see there will be a raw material is taken in the metal rod one, and another one you have the support material. So both you have one rod and one support, which you can see this is the model and this is the support, and you made differently. So now then you put it as a debinding. So it's like the third step is a debinding. So just you can remove your the second material. So you have used the support material or the binding material. So there you can debind that material. So then put it debinding station, you debind it, and next one is sintering. So then with the sintering step you can get 100% dense metal part. So then furnace treatment. So then your metal part is ready, right? So this is about the Desktop Metal. So where we can make a metal through FDM technology. So this is what where we can see. So this is the bottom support, and then this is the one where we can see the supports, and then you can remove those supports, and then finally you have this impeller metal out of FDM technology, right? So this is about a desktop metal, so which you can make metal also. So of course FDM, you have a different configured frames, like you have a Cartesian or a delta or normal typical XYZ movements like a Ultimaker or a rep wrap, or you have a different configurations. I'm talking about your degrees of freedom or how your XYZ can be moved. So you have a different configured machines, and of course you know how FDM works in the previous video also showing how it can be printed. So you bring the raw material in a filament, maybe thermoplastic, maybe PLA, ABS, PI, PEA, PC, and even metal ceramics and fiber filters. Just now we have seen in the previous video. So you have this, of course, PLA, Altem is the one material, lightweighting material, which you have more strength to weight ratio. That material is also possible. And of course, as we talked about, you have a thermoplastics. So like you have right from the PLA to Altem, nylon or TPU or any kind of a thermoplastic is one category. And just now we have seen the composites. So you have a nylon 12CF, or you have a embedded the materials which we discussed previously. So you can embed your you can reinforce with these composites, and then metal. So you can start with the metal rod as a raw material, and then you can end with your metal or your ceramic part like this. So, and of course the support structures, as we know that the supports are critical in any FDM machine, so which we need to talk, or we need to give a special care for the supports. So where you have some thumb rules to give the supports, so use that some thumb rules to give the supports, and you print the supports along with the model. So you may have a soluble support, or you may have a breakaway, whatnot, say, and then you can change the support structure, or like say you can play around it. And anyway, you are going to have some hands-on on the Cura software. So almost all these capabilities will be there in the Cura software. You can vary the infill density, so you can do several things. So utilize that Cura assignment properly. So you work all these, explore all these features in the Cura. That is a free of cost software, which I hope everybody has installed in your PC. So then, and of course you have the last one, even you can print the clay, like the ceramics, like a clay can be printed. You have through FDM technology, you have a direct writing of a clay paste. So 3D Potter board is a clay printer, one company, and then you have other. So these ceramic or a clay kind of a material which you will be taking in the form of a slurry, and then you will be depositing it. So of course the FDM of ceramics, so it can be done not directly after sintering. You are going to get this is a ceramic by weight. It is 80% of ceramics. So you have even debinding is sintering between 1200 to 1500 during your sintering process, and then you have a ceramic parts like this. So you, of course, you have a ceramic filament like alumina, zirconia, and you have a carbide like silicon carbide or silicon nitride, and you have a metals also, even stainless steel, tungsten carbide. So that is the development under this. So, and then even you can have a fiber layering, just now we discussed in the Markforged, and you have other technologies, other companies also, they can make the similar one for, especially if you take the Airbus case study here. So where you have a carbon fibers it's got blended onto the aircraft component. So this is the beauty. And you have a leaf fan blade from one of the aircraft case study where it got printed. Here we can see, and it's basically, it's like a woven kind of a mixing of these things, and then you are blending it. And of course earlier, which we have seen from the Markforged, the same way which they will be reinforcing, or rather than they will be printing these composites in that way. So of course the last one, in elaborate what this desktop metal, they are doing it as metal parts from FDM technology. So they're not calling as FDM as such. This is a bond metal deposition. So, and it should fall under the extrusion based system. That's what I kept this intentionally here this technology. It will write up to under this umbrella of FDM or extrusion based systems. So the raw material is not a filament here, it's a rod. So it is a metal rod. So you start printing the metal along with your support material or the ceramic or the polymer or whatever it is. Then you washed out or you debind that one and then put it in a furnace and get your 100% dense part. This is right now 316 steel, and they are saying that copper also they are able to print it. But as of now, they are saying that it is possible and they are doing it. But they have another system also. This is a studio system which is of binder, which is of FDM technology, and they have another kind of a thing called as a binder jetting. So under that, they have already made some copper parts. Copper is a material they have. As you know that copper is more challenging as of now. The 3D printing is concerned, but people are able to print the copper also. So no laser, no powder here, no powder, no laser, no infills, no sparse infills possible here, and you have a ceramic support, which release the layers and safe for the office environment. So you have, this is about the FDM metal. So in a recap, what we have done during this session, we have started with the classification of 3D printing processes, and we have highlighted the ASTM classification, that is a 7 groups. So right from the VAT to the DED system. But during this session, so we have talked about, say, starting with VAT photopolymerization process and material jetting process, binder jetting process, and FDM. So almost, so as I already mentioned, I want to make it as classification like a polymer printer and metal printer, composite or ceramic. I could not. Why? Because which we can see almost every technology is now capable of printing in polymer, ceramic, and metal. So with that, with this, I will hand over to the host.
So, okay, so thank you, Ravi Kumar, sir. It's a very nice session. So all participants, if you have any question, ask the sir, and have any questions, we can post in the chat box.
Good afternoon, Ravi Kumar sir. This is Prabhakar from NIT Warangal.
Yeah, Prabhakar, tell me.
Yes, sir. It's a nice presentation. Nowadays we have seen advancement in this 3D printing, especially metal jet printing.
Yes.
It's nice. Now, can you tell me, is the microstructure after the printed part is similar to a conventional casting component?
Yes, so studies are saying that, so the microstructural properties are on par with casted part. So it may be bit inferior than forging, but it is on par with the casting. So it is on par with the casting, the microstructural properties, and even you can make a monolithic structures which otherwise it may not be possible through conventional process. So it is on par with casting, sir. The microstructural properties are on par with casting, conventional casting. Yes.
Yes, good. Okay.
So any other questions?
Any questions?
In a chat box, any questions? Can you read out? If no more questions through oral, so then we can move on to the chat box questions.
There is no question till now in chat box also, sir.
Really? So,
Yes, sir.
Okay, then
So
can
we
we?
post the queue.
Pardon?